The dawn broke over the Pacific Theater on November the 24th, 1944, revealing a sight that would change the course of aerial warfare in ways no one could have anticipated. High above the Japanese home islands, formations of massive silver aircraft droned through the thin air at altitudes that seemed impossible just years before. These were the Boeing B-29 Super Fortress bombers, the most advanced and expensive weapon system ever created at that point in human history. Each aircraft represented a technological leap so significant that the entire Manhattan Project, which would ultimately create the atomic weapon, cost less than the B-29 program itself. But on this particular morning, one of these magnificent machines would not return home. Its story, and what followed, would expose a critical weakness that American engineers never anticipated, a vulnerability that Japanese technicians would exploit with devastating efficiency. To understand the significance of what was about to unfold, we must first appreciate what the B-29 represented. This was not simply another bomber. This was a pressurized, high-altitude flying fortress capable of carrying massive bomb loads across distances that defied belief. Its four Wright R-3350 duplex Cyclone engines, each producing 2,200 horsepower, could push the aircraft to speeds exceeding 350 miles per hour. Its service ceiling exceeded 33,000 feet, placing it beyond the reach of most Japanese fighters and anti-aircraft fire. The B-29 incorporated technology that seemed almost science fiction to those who first encountered it. Remote-controlled gun turrets allowed gunners to fire from sealed, pressurized compartments using sophisticated computing gun sights. The central fire control system could coordinate defensive fire with a precision never before achieved. The aircraft's pressurized cabin meant crews could operate at extreme altitudes without the debilitating effects of oxygen deprivation and extreme cold that plagued other bomber crews. American strategists viewed the B-29 as the ultimate strategic weapon, a bomber that could strike the Japanese homeland with impunity, systematically destroying industrial capacity and breaking the will to continue the war. General Curtis LeMay, commanding the 20th Air Force, had staked everything on these aircraft. They represented not just tactical superiority, but technological dominance, a demonstration that American industrial and engineering capabilities had reached a level Japan simply could not match. The aircraft that would change this narrative was part of a formation targeting aircraft manufacturing facilities near Tokyo. The crew had launched from their base in the Mariana Islands before dawn, joining dozens of other super fortresses for the long flight to the target. The mission profile was standard: climb to bombing altitude, navigate to the target using the sophisticated radar and navigation systems, deliver the payload, and return home. The crew was experienced, having flown multiple missions over Japan. They knew the risks, but trusted their aircraft absolutely. The flight to the target proceeded normally. The formation maintained tight discipline as they approached Japanese airspace. Anti-aircraft fire began to explode around them as they neared the target, black puffs of smoke appearing seemingly from nowhere, each one capable of tearing through aluminum skin and flesh with equal ease. The pilots maintained steady course, knowing that evasive maneuvers would compromise bombing accuracy. Then, without warning, something went catastrophically wrong. The number 3 engine, the inboard engine on the right wing, began to malfunction. Pilots of other B-29s in the formation would later report seeing smoke trailing from the stricken aircraft. The engine temperature gauges in the cockpit went into the red zone. Within seconds, flames were visible, licking along the engine cowling. The pilot, a captain from Ohio with 24 missions under his belt, immediately initiated emergency procedures. He feathered the propeller, cutting fuel flow to the engine and activating the fire suppression system. For a moment, it seemed the fire might be contained. But the B-29 had a secret weakness, one that Boeing engineers knew about, but had never fully resolved. The engine installation, while revolutionary in its power and efficiency, created a thermal management challenge unlike anything previously encountered in aircraft design. The Wright R-3350 engines ran extremely hot. In the tight nacelle installation required for the B-29's aerodynamic profile, heat management became critical. The magnesium alloy components used throughout the engine and nacelle, chosen for their excellent strength-to-weight ratio, had one fatal characteristic. Once ignited, magnesium burns with intense heat and is nearly impossible to extinguish with conventional firefighting methods. It produces its own oxygen as it burns, meaning even cutting off external oxygen supply does little to stop the reaction. As the crew watched in growing horror, the fire spread despite their best efforts. The flames moved from the engine into the wing structure itself. The fire suppression system, designed for conventional fuel and oil fires, proved ineffective against burning magnesium. Within minutes, the entire engine nacelle was engulfed. The structural integrity of the wing began to fail as supporting members weakened in the intense heat. The pilot had no choice. The aircraft was over Japanese territory, losing altitude, with a fire that threatened to consume the entire wing structure. He gave the order he had hoped never to give. The crew would abandon the aircraft. One by one, the men moved to the bomb bay, now empty of its deadly cargo, and jumped into the hostile sky below. The bomber, relieved of its human cargo and still partially under control, continued to descend. It came down in agricultural land outside a medium-sized industrial city. The impact was violent but not catastrophic. The fuselage remained largely intact. Most importantly, for what would follow, the fire had not spread to the center sections of the aircraft. Much of the superfortress's revolutionary technology survived the crash. Japanese military authorities received word of the downed American bomber within hours. This was not the first B-29 to fall on Japanese soil, but each capture represented an intelligence opportunity of immense value. Orders went out immediately. The wreckage was to be secured and preserved. A team of technical experts would be dispatched from Tokyo to conduct a thorough examination. The team that arrived 3 days later represented some of Japan's finest aeronautical minds. Engineers from Nakajima and Mitsubishi, the nation's primary aircraft manufacturers, joined military technical officers and specialists in various aviation systems. They came with a clear mandate: examine every aspect of this aircraft, understand how it works, identify weaknesses, find ways to counter it. The Japanese engineers approached the wreckage with a mixture of professional curiosity and barely concealed awe. They had heard reports about the B-29's capabilities, but seeing the aircraft up close was something else entirely. The sheer size impressed them first. Japanese bombers seemed like toys in comparison. The skin was thicker than expected, the structural members heavier. This was an aircraft built for durability and survivability, but it was when they began detailed examination that the true sophistication became apparent. The remote gun turret systems fascinated the engineers. Japanese aircraft relied on manually operated guns, requiring gunners to brave the elements and operate weapons with freezing hands. Here was a system where gunners sat in comfortable, pressurized compartments, manipulating controls that aimed and fired weapons through an analog computer system. The precision was remarkable. The radar equipment, though damaged in the crash, revealed capabilities Japanese forces had only suspected. The Americans had miniaturized radar technology to a degree Japan had not achieved. This explained how B-29s could navigate and bomb through cloud cover, finding targets Japanese defenses assumed were protected by weather. The pressurization system drew intense scrutiny. Japanese engineers understood the theory, but implementing it in a combat aircraft at this scale exceeded their current capabilities. The complexity of seals, the redundancy of systems, the integration with oxygen supply, It all represented engineering at a level that forced grudging respect. However, it was a relatively junior engineer, a specialist in power plant systems from Nakajima, who made the most significant discovery. He had been assigned to examine the engine installation, specifically the burned engine that had brought the aircraft down. As he carefully documented the fire damage, something caught his attention. The pattern of burn marks and structural failure told a story. He called over his supervisor and pointed to the magnesium alloy components in the nacelle. Through an interpreter, since detailed technical discussion required precision, he explained what he was seeing. The fire had started in the engine, but had been catastrophically amplified by the magnesium structures. He noted the relatively small fuel spillage, yet the massive structural damage. This was not a fuel fire. This was magnesium burning. The senior engineer immediately understood the implications. He ordered a complete examination of all 4 engine nacelles on this aircraft and requested any reports on other downed B-29s. Over the following weeks, a picture emerged that shocked Japanese military leadership. The B-29, for all its sophistication and power, had a fundamental vulnerability. Its engines, pushed to the limits of contemporary technology to achieve the performance required, ran hot enough that any malfunction could trigger catastrophic fires. The magnesium components, while necessary to keep weight down, turned each engine nacelle into a potential incendiary device. Japanese engineers compiled detailed reports. They noted that the fire suppression systems, while present, seemed inadequate for magnesium fires. They documented the proximity of fuel lines to hot engine components. They identified the most vulnerable points in the nacelle structure. This intelligence was immediately classified at the highest level and distributed to fighter commands throughout Japan. The impact was immediate and devastating. Japanese fighter pilots received new tactical guidance. Previous instructions had emphasized attacking B-29s from below and behind, targeting the tail and fuselage. The new directive was specific. Target the engines. Concentrate fire on the engine nacelles. Even if you cannot score killing hits on vital components, any damage that leads to overheating or fuel leaks will likely result in uncontrollable fires. The specially formed B-29 hunting units began to see results. The Kawasaki Ki-61 fighters, armed with cannons and operating at high altitude, found they could inflict critical damage with relatively brief firing passes. The Nakajima Ki-84, though slower than the B-29, could match its altitude and had the firepower to savage engine nacelles. American bomber crews began reporting a disturbing trend. Engine fires, previously rare, became increasingly common. Aircraft that survived the initial damage from fighter attacks found themselves fighting, losing battles against spreading flames. Loss rates climbed. Crews that had felt relatively invulnerable in their high-tech fortresses now faced a new reality. Their supposedly impregnable bomber had an Achilles heel. The American military establishment initially struggled to understand what had changed. Intelligence analysts noted the shift in Japanese tactics, but initially attributed it to improved fighter performance or pilot training. It took several months before the pattern became clear enough to trigger serious investigation. When technical teams finally examined aircraft that had survived engine fires, they confirmed what the Japanese had discovered. The combination of extremely hot running engines, magnesium construction, and the pressures of combat operations created a vulnerability that theoretical testing had not fully revealed. Boeing engineers, when confronted with the evidence, acknowledged they had been aware of the thermal management challenges, but had believed their solutions adequate. The fire suppression systems had passed all tests. The engine installation had been analyzed extensively, but laboratory conditions could not fully replicate combat stress. An engine damaged by enemy fire behaved differently than one failing under controlled test conditions. Fuel and oil leaks under combat damage scenarios exceeded design assumptions. A crash program began to retrofit B-29s with improved fire suppression systems. Modified engine installations with better thermal barriers were designed. Crews received updated emergency procedures for engine fires, emphasizing the need to abandon the aircraft quickly if fires could not be controlled within the first minute. But these were all reactive measures attempting to patch a fundamental design compromise that had been baked into the aircraft from the beginning. The story took another turn as American intelligence began to piece together how Japanese fighters had suddenly become so effective against B-29 engines. Interrogations of captured Japanese pilots revealed the technical analysis of crashed B-29s. American technical intelligence teams managed to obtain some of the Japanese reports through various channels, though details remained murky. What became clear was that the Japanese had conducted systematic, professional analysis of captured technology and had rapidly translated that analysis into tactical advantage. The same methodical engineering approach that had produced the Zero fighter in the late 1930s had been applied to understanding and countering the B-29. This revelation sparked debate in American military and political circles. Some argued for increased security measures to prevent intact aircraft from falling into enemy hands. Crews were instructed to avoid Japanese-controlled territory when possible and to destroy their aircraft if capture seemed inevitable. But the reality of aerial combat made such instructions difficult to follow. When an aircraft was on fire at 25,000 feet over Japan, the crew's priority was survival, not the long-term security implications of the wreckage. The Japanese discovery and exploitation of the B-29's vulnerability had broader implications for the air campaign against Japan. General LeMay, never one to shy from difficult decisions, made a choice that would define the final months of the war. If the B-29s could not operate with impunity at high altitude, he would send them in at low altitude, at night, loaded with incendiary weapons, rather than high explosives. This shift in tactics, driven in part by the vulnerability the Japanese had exploited, would lead to some of the most devastating air raids in history. The firebombing campaign against Japanese cities, while horrifically effective, was also far more dangerous for American crews. Flying at low altitude removed the altitude advantage that had been central to the B-29's design philosophy. But it also made the aircraft faster and more maneuverable, partially offsetting the engine vulnerability that had been so costly at high altitude. The engineers on both sides continued their deadly chess match. Japanese designers worked on new fighters optimized for attacking B-29s. They experimented with heavy cannons, air-to-air rockets, even ramming tactics. Each new weapon or tactic was designed to exploit what they now understood about the bomber's weaknesses. American engineers pushed forward with improvements. New engine installations with better fire protection gradually filtered into the fleet. Improved firefighting systems gave crews a better chance of controlling engine fires. Tactical formations were adjusted to provide better mutual defense. But these measures were evolutionary, not revolutionary. The fundamental design of the B-29 could not be changed in the middle of a war. The human cost of this technical battle was profound. Every B-29 that went down in flames represented 11 highly trained crew members, men who had spent months learning to operate the most complex aircraft of their era. Some crews managed to bail out over Japanese territory, facing capture and uncertain treatment. Others rode their burning aircraft down, unable or unwilling to abandon ship. Still others made it back to base, their aircraft so damaged that they were scrapped upon landing. Japanese pilots paid their own price. Attacking a B-29 formation was dangerous work. The bomber's defensive armament, while not perfect, could still tear a fighter apart. The heavily armed B-29 hunting fighters sacrificed speed and agility for firepower, making them vulnerable to American escort fighters when those began to appear over Japan. and focusing attacks on engines meant closing to effective gun range, where both bomber and fighter guns could be devastating. The psychological impact on both sides was significant. American crews, who had initially viewed the B-29 as nearly invulnerable, now flew with the knowledge that their aircraft had a critical weakness. Pre-flight briefings included detailed instructions on engine fire procedures. Crews became hypervigilant about engine temperatures and any signs of malfunction. The stress of watching engine gauges while also dealing with enemy fighters and anti-aircraft fire took its toll. Japanese defenders, meanwhile, gained confidence from their discovery. The B-29 was not invincible. It could be beaten. This knowledge sustained them through the increasingly desperate final months of the war, even as American air superiority became overwhelming. Fighter pilots who scored engine hits watched with grim satisfaction as massive bombers began their fatal descents, trailing smoke and flame. The technical intelligence coup that Japanese engineers achieved through their systematic examination of the downed B-29 represents a fascinating case study in how intelligence and analysis can shift military balance. The Japanese were not merely lucky to find a weakness. They actively looked for it. They brought together the right expertise. They analyzed methodically. They translated their findings into actionable intelligence quickly, and they distributed that intelligence effectively to the forces that could exploit it. This stands in contrast to other instances in the war where captured technology sat in warehouses, examined cursorily or not at all. The Japanese, facing overwhelming American material superiority, understood that any advantage, no matter how small, had to be exploited fully. The engine vulnerability was exactly the kind of asymmetric advantage that could partially offset American numerical superiority. From an engineering perspective, the B-29 vulnerability highlights the challenges of pushing technology to its limits. Boeing's designers were working at the edge of what was possible with 1940s materials and manufacturing techniques. The Wright R-3350 engine represented a masterpiece of mechanical engineering, extracting enormous power from a relatively compact package. But this performance came with inherent risks. The use of magnesium alloys throughout the aircraft was similarly driven by the demanding requirements. The B-29 needed to be strong enough to survive combat, large enough to carry meaningful bomb loads across vast distances, yet light enough to reach high altitudes and achieve respectable speeds. Magnesium offered the strength-to-weight ratio that made this possible. That it also burned fiercely when ignited was a known drawback, but one that designers felt they could manage. In the controlled environment of flight testing and acceptance trials, the fire suppression systems worked. Engine failures were managed successfully. But combat introduced variables that testing could not fully anticipate. Battle damage created fuel and oil leaks in ways that test scenarios did not replicate. Damaged engines ran hotter and less efficiently. Fires started in locations where fire suppression systems were less effective. The statistical probability of cascading failures increased dramatically. The Japanese discovery forced American planners to confront uncomfortable questions about the B-29 program. Billions of dollars had been invested in developing and producing these aircraft. Strategic plans for defeating Japan relied heavily on the B-29's ability to systematically destroy Japanese industrial capacity. If the losses became unsustainable, those plans would collapse. The decision to shift to low-altitude night incendiary attacks, while driven by multiple factors, was influenced significantly by the high-altitude daylight bombing losses. The new tactics required completely different crew training, different bomb loads, different formation procedures. In essence, the B-29 was being used in a role quite different from its original design purpose, largely because its intended role had become too costly. The irony is that the low-altitude tactics, while more dangerous in some ways, actually reduced the impact of the engine vulnerability. At lower altitudes, Engines ran cooler. The air was denser, providing better cooling. Engine fires, while still dangerous, were somewhat less likely to become uncontrollable. And if an aircraft had to be abandoned, crews had a better chance of survival at 10,000 feet than at 30,000. The Japanese engineers who made the initial discovery likely never knew the full impact of their work. In the chaos of late-war Japan, with the situation growing more desperate by the month, the focus was on immediate survival rather than analysis of cause and effect. The increased B-29 losses they caused were just one factor among many in the complex calculus of aerial warfare. Some of those engineers would survive the war and go on to contribute to Japan's post-war aviation industry. The analytical skills they demonstrated in examining the B-29 would serve them well in rebuilding Japanese aerospace capabilities. Others would perish in the final months of fighting, their contributions lost to history, except for the classified reports they authored. On the American side, the lessons learned from the B-29's vulnerabilities would influence post-war aircraft design significantly. The next generation of strategic bombers would incorporate redundant fire suppression systems, improved engine fire barriers, and more conservative thermal designs. The push for ever higher performance would be tempered with greater attention to survivability and fault tolerance. The crews who flew the B-29s during the period when the vulnerability was being most heavily exploited showed remarkable courage. They knew their aircraft had a critical weakness. They knew that Japanese fighters were specifically targeting engines. Yet they continued to fly mission after mission, trusting in their training, their aircraft's other capabilities, and each other. The maintenance crews who kept the B-29s flying also deserve recognition. They worked around the clock to install improved fire suppression systems, to repair battle-damaged aircraft, and to keep engines running despite the extreme demands placed on them. They understood the technical challenges intimately and did everything possible to give the flight crews every advantage. As the war moved into its final phase, the strategic bombing campaign against Japan intensified. The engine vulnerability, while never fully solved, became less significant as American air superiority became absolute. With fewer effective Japanese fighters able to reach attacking bombers, engine fires from combat damage became less frequent. The vulnerability was still there, but the opportunities to exploit it diminished. The introduction of atomic weapons in August 1945 rendered much of the technical back and forth moot. The B-29, despite its vulnerabilities, proved capable of delivering the weapons that ended the war. The Enola Gay and Bockscar, the aircraft that dropped the atomic bombs on Hiroshima and Nagasaki, completed their missions without incident. The engine vulnerability that had cost so many lives over the previous months was irrelevant to those final, terrible missions. In the decades since the war, the story of the Japanese discovery of the B-29's engine vulnerability has been overshadowed by more dramatic narratives. The atomic bombs, the firebombing of Tokyo, the kamikaze attacks. These are the stories that dominate the historical record. But for those who flew and maintained the B-29s, and for the Japanese defenders who fought against them, the engine vulnerability was a defining characteristic of the air war over Japan. Modern analysis of the B-29 program acknowledges the engine fire issue as a significant design flaw, one that cost lives and forced tactical adaptations. Yet it also recognizes that the aircraft, despite this weakness, remained an effective strategic weapon. The B-29 delivered more than 170,000 tons of bombs on Japanese targets. It helped bring about the end of the war in the Pacific. Its technological innovations influenced aircraft design for decades. The Japanese engineers who examined that crashed B-29 in late 1944 were doing their duty, applying their professional skills to support their nation's war effort. They could not have known that their careful analysis would influence tactical decisions that would lead to the loss of dozens of aircraft and hundreds of crew members. They were simply doing what engineers do, examining evidence, drawing conclusions, making recommendations. The vulnerability they discovered was real and significant. It was not a propaganda invention or an exaggeration. American records confirm the increased loss rates and attribute them in part to Japanese fighters concentrating on engine attacks. The retrofit programs undertaken to address the vulnerability consumed resources and time. The shift to low-altitude tactics, while driven by multiple factors, was influenced by the losses occurring at high altitude. This episode in military history illustrates several enduring truths about warfare and technology. First, even the most advanced systems have weaknesses. The B-29 represented the cutting edge of aerospace technology, yet it had a vulnerability that could be exploited by a determined and analytically capable enemy. Second, intelligence and analysis matter. The Japanese did not stumble on the vulnerability by accident. They systematically examined available evidence and drew correct conclusions. Third, vulnerabilities in isolation do not determine outcomes. Despite the engine fire issue, the B-29 remained a war-winning weapon system. For students of engineering and military history, the B-29 engine vulnerability offers lessons about the challenges of designing complex systems under wartime pressures. Boeing's engineers made reasonable choices given the requirements and technology available. The use of magnesium and the tight engine installation were necessary to achieve the performance demanded. That these choices created a vulnerability was unfortunate, but perhaps unavoidable, given the state of technology in the early 1940s. The story also highlights the importance of operational testing and combat experience in revealing system weaknesses. Laboratory testing and flight trials had not revealed the full extent of the fire vulnerability. It took the stress and chaos of combat operations combined with enemy action specifically targeting engines to expose the issue. This remains relevant today, as complex military systems often reveal unexpected vulnerabilities when employed in actual conflict rather than controlled test scenarios. For the men who flew the B-29s, the engine vulnerability was not an abstract technical issue. It was a life-or-death reality. They developed superstitions about engine fires. They watched their gauges obsessively. They knew which engines on which aircraft had histories of problems. This folk knowledge, passed between crews, represented a parallel form of intelligence gathering, one driven by survival instinct rather than formal analysis. The families of crew members who lost their lives to engine fires likely never knew the technical details of why their loved ones died. They received telegrams stating that aircraft were lost over Japan, that the crew did not survive. The specific cause, whether anti-aircraft fire, fighters, mechanical failure, or some combination, was often unclear. The distinction between dying because of a general vulnerability versus dying for other reasons probably seemed academic. The loss was absolute regardless. As we reflect on this chapter of World War II history, we must remember that behind every technical failure, every vulnerability exploited, every tactical adaptation, there were human beings. Young men far from home, flying complex machines in incredibly dangerous circumstances. Engineers on both sides working to give their nation's forces every possible advantage. Families waiting for news that might never come or that would bring unbearable grief. The B-29 engine vulnerability discovered by Japanese technicians examining a crashed bomber represents a small but significant thread in the larger tapestry of the Pacific War. It influenced tactics, caused losses, forced adaptations, and ultimately became part of the complex calculus that determined how the air war was fought. It reminds us that in warfare, victory often goes not to those with perfect weapons, but to those who can identify and exploit enemy weaknesses while minimizing their own vulnerabilities. The crashed B-29 that Japanese engineers examined so carefully in late 1944 was eventually scrapped, its valuable aluminum recycled for Japan's desperate war effort. The engineers' reports were likely destroyed in the final chaotic weeks of the war, either deliberately to prevent them falling into American hands or simply lost in the general destruction. The crews who flew B-29s during that period mostly returned home after the war, their experiences becoming private memories rather than public history. But the legacy of that discovery lives on in the cautionary tale it provides about the limits of technology and the importance of thorough technical intelligence. It reminds us that in the brutal calculus of warfare, knowledge can be as valuable as weapons, that careful analysis can yield advantages that brute force cannot, and that even the mightiest weapon systems can harbor fatal flaws waiting to be discovered by determined enemies. The B-29 may have been a marvel of engineering, but it was also a product of compromise and limitation, a reminder that in war, as in all human endeavors, perfection remains forever elusive.